All right, let's talk about an idea that sounds like it's straight out of a sci-fi movie. What if we could build giant machines to literally vacuum carbon dioxide right out of the sky? It's a technology called direct air capture, or DAC, and it offers a pretty direct, though maybe not so simple, solution to a massively complex problem. I mean, the idea itself feels so simple, right? For more than a century, we've been pumping CO2 into the air. So, what if we can just hit reverse? Could we build something that does what trees already do, but maybe way faster and on a much bigger scale? At its core, the whole idea of direct air capture is just really intuitive. And what makes it so appealing is that it's not just about stopping future pollution, it's designed to go after the emissions that are already up there, warming our planet right now. You can basically think of these things as giant artificial trees. The whole point is to have these huge facilities that pull in enormous amounts of air, scrub out the CO2, and then push cleaner air back out. It's engineering trying to mimic a natural process, but on steroids. But how do you actually build an artificial tree? Well, the engineering behind this is pretty fascinating, and right now there are two main ways people are trying to do it. Now, we've got to be super clear about one thing here. This is not about capturing smoke from a smokestack. That's a different thing called point source capture. No, DAC is about grabbing the CO2 that's already mixed into our entire atmosphere everywhere. So it boils down to two leading methods. One approach uses liquid solvents, where air is bubbled through a chemical solution that just soaks up the CO2. The other uses solid materials, kind of like a filter, that the CO2 molecules stick to as the air passes over them. Either way, you then have to use heat to release that captured CO2 so you can collect it and store it. Okay, so the technology sounds pretty cool, right? Well, this is where the dream crashes into reality. The sheer scale of the problem we're trying to solve is, well, it's almost impossible to wrap your head around. 10 gigatons. A gigaton is a billion metric tons, and that is the amount of CO2 we need to remove from the atmosphere every single year from now until 2050, just to meet our climate goals. That number comes from the National Academies of Sciences. It's just huge. So how do you even get to that 10 gigaton number? Well, to do that, we would need to build and run about 13,000 massive large-scale DAC plants. We're talking about creating an entirely new global industry, basically from nothing. And the price to just build them? The construction alone is estimated at $1.7 trillion. And remember, that doesn't even count the huge ongoing costs for the energy to run them, the staff, or, actually storing all that carbon you capture. And just to put the physical size into perspective, the land you'd need for all those plants would cover an area nearly 7 times the size of New York City. This is an industrial rollout on a scale we've rarely seen before. This quote really hits home just how big the challenge is. Think about it. For every liter of gas we burn in our cars, we create roughly a liter of CO2 gas that has to be captured and then put somewhere. The scale of our emissions has a direct one-to-one consequence for the scale of the cleanup. Which brings us to probably the biggest hurdles for direct air capture, the incredible amount of energy it takes to run, and the absolutely astronomical costs that come with it. So here's the fundamental physics problem. CO2 is incredibly diluted in the atmosphere. It's like 420 parts per million. That's like trying to find a few specific grains of sand on an entire beach. Pulling CO2 out of this dilute mix takes about 3 times more energy than capturing it from a concentrated source, like a power plant smokestack. It's just a law of thermodynamics, and it makes the whole thing inherently expensive. And even when you power these plants with clean energy, which you have to, right? Otherwise, what's the point? The costs are still really high. With geothermal, which is the cheapest option, you're still looking at hundreds of dollars per ton of CO2. With solar, it could be almost $700 a ton. And get this, capturing the CO2 is only half the battle. You then have to permanently store it, usually by pumping it deep underground. And the cost to do that, to build the pipelines and run the injection wells, could end up costing as much as the fossil fuel that created the problem in the first place. So you're basically doubling the price of that energy. This leads us to a really big criticism, that DAC could just be a form of greenwashing. Critics point to examples where captured CO2 is sold to, say, a greenhouse to help plants grow faster. But the problem is that CO2 just goes right back into the atmosphere when the plants are eaten or decomposed. The fear is that this lets companies look like they're taking climate action without actually making the deep cuts in their own emissions that we really need. So where does that all leave us? Is direct air capture a crucial tool that we absolutely have to have in our climate toolbox, or is it just an incredibly expensive, impractical dream? The debate really falls into two camps. On one side, you have supporters who say that for industries like aviation or making cement, stuff that's really, really hard to decarbonize, DAC is essential to cancel out their emissions. But on the other side, critics say the technology is just financially dead on arrival, a dangerous distraction from the real work of cutting emissions now. Maybe the best way to frame this whole debate is as an issue between generations. As one analyst put it, we've basically been the party generation, enjoying a century of cheap energy. But there's going to be a hangover generation. And they won't just have to pay the true cost of their own energy. They'll also have to pay to clean up our mess. Which really brings us to the final question. Is direct air capture a responsible, necessary cleanup tool that we owe to future generations? Or is it a convenient fantasy, a seductive solution that just lets us kick the can down the road and avoid the much harder choices we need to be making right here, right now? The answer to that is going to shape the world for decades to come.